Hi, I'm Bhargav Shivkumar and I will be talking about the Isabelle Theorem Prover. I will be giving you a little tutorial on what the Isabelle Theorem Prover is and how to use it to write a small functional program and to prove its correctness. Let me start off by telling you what Isabelle is. Isabelle is basically an interactive theorem prover which is written in standard ML. Standard ML is a functional programming language that was written mainly keeping in mind proving theorems in Isabelle and LZF, and it was written to support these proofs. And Isabelle, when I say is an interactive theorem prover, I mean to say that it's not autonomous completely. It needs some sort of interaction from a human in order to get more information to solve a theorem that you're trying to prove. So it was developed mainly at the University of Cambridge, at the University of Cambridge by Larry Paulson, Tobias Nipkow, among others. It is a generic system which is used for specification, and it is used as a specification and a verification system, and for implementing logical formalisms. And ISAR is the proof language that is used to structure the proofs written in Isabelle. And one advantage of this language over other theorem provers like COQ is that theorems presented in ISAR are much more human readable, and Isabelle has various applications in the industry, and it has also been used for formally verifying parts of the JVM. And there's a list of things that have been done with Isabelle. So a little anecdote maybe on why the name Isabelle. I was wondering on what it was, whether it was an acronym for something or what it stood for. So I asked the author Larry Paulson on why it was Isabelle, and this is what he had to say. So I guess that we might not find out what Isabelle stands for after all. Moving on, Isabelle uses HOL, which is a higher order logic. This logic is used for expressing the programs in Isabelle, and we model functions with HOL, which can then be proved using Isabelle. And any sort of theorems that we write, the logic is basically written in the HOL syntax. And since Isabelle is built on ML, HOL syntax is very similar to ML. So if you know SML, this would be pretty intuitional as well. So in this tutorial, I will be talking about writing a program using HOL, and I will explain a little bit on the syntaxes and semantics of HOL as and when I am showing you the demo. So let's go ahead and see how we could write a functional program and prove its correctness on the tool. So this is the Isabelle homepage. This has a lot of information on what Isabelle is and how to use it. It also gives you the download files for Isabelle, for setting up Isabelle on your system. It has versions for Linux, Windows, and Mac OS X. You could download it from here, and the installation instructions are given pretty clearly, and you shouldn't have any problems installing Linux. I'm sorry, installing Isabelle on any operating system. And there's a lot of information on here regarding troubleshooting of any problems that you may have while installation, and the community also has a lot of information that is useful when you are writing theorems, and you have some questions related to that. So this is something worth looking into. So let's move on to how you would use the tool in itself. Okay, in order to start Isabelle in Linux systems, you could open out a terminal, and once you're done with the installation, you can just say Isabelle 2015 slash Isabelle 2015, and this is going to open up the JEdit IDE for developing theorems in Isabelle. So one little thing I want to say here is, before using this JEdit software, there used to be a plugin for Emacs called Proof General, which is pretty widespread, but as of now, Isabelle community has stopped any support for Proof General, because this seems to be a much better IDE for proving theorems, or for using Isabelle in general. So when we open up Isabelle, Isabelle first opens up to scratch.thy file, which is like a scratchpad. But any theorems written in Isabelle must have the same name, as a file name should be the same name as a theorem name, which is a prerequisite. So let me go ahead and create a theory and call it test reverse. Okay, let me first do this. Let me create a new file, and I will name the theory test reverse list, and I will say imports main begin, and let me save this file as a new file, and we'll save it here. I will call this the same name. I will call this the same name as my theory name, so this should be test reverse list.thy, and it will create a new file for me. So the example that I'm taking up here is the reversal, a function that will reverse the list. And I will first write this function, and then I will go ahead to write a theorem to prove the correctness of this function, and thereby demonstrating how Isabelle works as well. So as you say, as you see here, there's this statement that says imports main. So main is actually a main theory or main theorem which is there in the libraries of Isabelle, which contains all the basic theorems that we might need or we might use to solve our theorems that we write. So it has theorems about lists, about numbers, about sets, and all the basic theorems that have already been proved are present in this, and we could import this and use those theorems to help prove any theorems that we may write. So whenever you're working with Isabelle, it's good to include this main. If you know what you're doing, that's fine. If you don't want to include it, that's fine. But otherwise, it's good to include this in your theorem. So let me go ahead and paste the um, function to traverse a list, and then I could go ahead and explain it for you. So this is the function to reverse a list, and as you see over here, data type list defines two data constructors, nil and cons. Nil is an empty list, and cons is the an operator that adds an element to the start of the list. So any list that is defined with this data type will have it'll have a syntax like, say, cons true, cons false, nil, which is a list that contains true and false. As you see, this is not very intuitive, so I will go ahead and I will define two operators as infix operators for nil and cons, so that I could go ahead and define lists more intuitively, like, say, this syntax over here. So in this statement over here, I say whatever notation is there for nil and cons, replace it with these infix operators, and the infix r command tells me that these infix operators are right associative, and the priority for these operators are at 65. And so we can go ahead and define lists more intuitively. So, and this statement, height type list, and tells Isabelle that if there are any other theorems having the data type list, which has been imported through this imports main command, ignore that and use whatever list definition I'm giving currently in this file. So, and hide const rev does the same thing. If in case there's any reverse that has been, or rev that has been defined earlier, it would ignore that and use the current function definition for rev. So these two functions, primrec_app and primrec_rev, are pretty self-explanatory. They are recursive function. Appends an element to the list, and reverse, when passed a list, gives you the reverse of the list. And this is pretty much how you would define the reverse and the append function in any functional programming languages. So if you are used to functional programming language, this would be a very familiar syntax for you. So now that these functions have been defined, Isabelle would have already parsed this, and you can go ahead and test these functions. So I can test these functions by giving a value, rev, true, false. And this is basically a list that has true and false. So the reverse of this should be computed. So I'm gonna just place my cursor on here, and Isabelle's gonna parse that line, and it's going to give me the reverse of this list, which is false true. And similarly, I could also not pass a boolean or an integer. I could also pass a symbolic value, like say just A, B, and C, which is something like a symbolic execution, not particularly symbolic execution, but a pseudo symbolic execution maybe, where A, B, and C could be any identifier. It need not necessarily be a data type variable. It could be just any identifier, and HO and Isabelle would still give me the output, because HOL is more than just a functional programming language, it's more of a specification language. So I can do small symbolic executions of these sorts using whatever functions that I've written in the HOL syntax. So just a little syntax sugar. Anything that is written inside these quotes is HOL syntax, and anything that is written outside of it, like say primrec and hide const, all of these are ISAR primitives or ISAR commands that tell ISAR how to process whatever is coming forward in the logic. So all my logic is within quotes, and anything that I need to tell Isabelle to do is particularly outside of the quotes and specified in ISAR. Okay, so now I've written my program to reverse a list, but the main functionality of Isabelle is to prove the correctness of this program and not just to write the program. So let us go ahead and write a theorem to prove that whatever function or whatever program that I've written here is correct, or whatever program I've modeled here would be the right word, is correct. So let me go ahead and so the program written here is to reverse a list. So if I can prove that the reverse of the list is the original list itself, then I can consider that my program is correct, right? So that's what I'm going to go ahead and do. I'm going to try to prove that calling reverse twice on any list given gives me the original list. If that can be proven, then whatever program I've written is right. So I'm going to say theorem rev simp reverse of a list is the list itself. So this theorem command tells Isabelle to do many things. For first, it tells that I'm defining a theorem and calling it reverse underscore reverse, and this bracketed attribute simp tells that this theorem is a simplification rule. So once this has been proven correct, you can use this as a simplification rule for any other theorems. And this is what the theorem states, that is the reverse of a list is the original list in itself. So let us tell so the best way to prove any recursive function is by applying induction on that function. So let us tell Isabelle to apply induction to see if it can prove this theorem that we wrote on itself. Apply auto done. Okay, so what I said over here, I told Isabelle to apply induct underscore tac, which is a tactic, and these tactics are usually written in SML, as I said earlier. So induct tac is a tactic that applies induction on the given variable, and we apply induction on the variable xs over here and try to simplify it further to see if we can prove that reverse of a list is in fact the list in itself. And apply auto is a command that tells Isabelle to apply this induction. So Isabelle, when I give it this, when I tell Isabelle to write to prove this theorem, it tells me that I do not have enough information, and in order for me to prove this theorem correct, I need this following subgoal to be proved. So, or I need more information to prove this following subgoal. So what does this subgoal say? The subgoal says that for all bounded variables x1 and x2 in this context, reverse of given, this is the assumption, given that reverse of x2 is x2, and this is the conclusion. That is to say that the reverse of x2 appended to x1 is x1 hash x2 x1 cons x2. So basically it's trying to ask us that there is no intuitive definition for reverse of an appended list, and thus it needs more information for being able to say that the reverse of an appended list is the original list itself, for which we would have to write in a supporting lemma for this. So clearly this theorem isn't done, so I am going to say oops, it's not done. So I need to define another lemma to help solve this theorem. So something that suggests itself is a lemma that says how to reverse appended lists. So I'm going to go ahead and define this lemma. Is reverse of ys appended to reverse of xs. So this is, we know, as you know, when we see the function definition, we know that this is how the reverse of an appended list would be, is the reverse of the tail and then appended to the reverse of the head, because the head and tail might be lists in itself. So we tell Isabelle to apply induction automatically on xs. So here we could choose xs or ys, but we apply induction on xs because append is defined recursively to the left. So we recursively define append on the left variable, and hence we say apply induction on xs, and we say apply auto and done. But when I say when I say apply auto, it sees that it's still not done. It needs more information in order to be able to prove even this lemma. So so what we do over here is that we see that there are two things. So over here, when we do apply auto, there isn't even a base case that's solved. The trivial case over here isn't solved as well. So we have two sub goals now. One that says this talks a little bit about the properties of appending an empty list to a list, which we haven't obviously defined over here. We've defined the reverse. I'm sorry. We've defined how it would act when you append a variable. I'm sorry. An element to an empty list, but you don't have the definition for appending an empty list to a variable. So we're gonna need another lemma or two more lemmas to help us solve each of these sub-goals separately. So let me first go ahead and solve the first sub-goal, which is trivial. Let me write a lemma. So yes, coming here, it's not obviously done, so I say oops. Oops basically is a command that tells Isabelle that this proof is not yet done, and I'm writing something further to help solve this proof. So I'm going to write another lemma to solve the first sub goal, that is this one. So I am going to call this lemma app no. Then I'm going to say that it's in a simplification attribute, use it as a simplification, and xs appended to an empty list is xs itself. So if you append an empty list to a list, you're getting the same list itself. So when I'm going to again apply induction on xs and say apply auto. And now it proves, it says this is trivial enough for it to be able to prove on its own, and thus it says that we have no subgoals, and so this lemma is done. So when we go back here to this lemma that we wrote, the first lemma that we wrote, we find that the first subgoal has been solved with the help of this lemma, and the second subgoal remains. Now, if we just take a look at this subgoal, we can see intuitionally that it talks about the associativity of the append operator, and we do not go ahead to specify any associativity of how the append works. So this is intuitional in saying that we need to write a lemma that tells us about the associativity of the append operator. So let me go ahead and define another lemma, call it app associativity, say that it is a simplification rule, and I'm going to define it as xs appended to ys, which is then appended to, say, zs, is the same as xs appended to ys appended to zs, which is just a simple associativity rule. A appended to b appended to c, a appended to b, which is then appended to c, is the same as a appended to b appended to c. I mean, I guess you could figure out where the brackets appear. So I'm going to say apply induction tactic on xs, again because append is defined in recursion on the leftmost element, and say apply auto and done. So we can see that okay, this should be okay. So we say apply auto, and there is no subgoals, and so this has been proved in itself. And due to these two lemmas that we currently defined, we could come here and see that we have solved this lemma that we wrote as well. So this has no subgoals to prove, so we can say this is done. And then because these lemmas have been proved, we can come here and see that we can prove this theorem that we originally wrote as well. So with the help of the above defined lemmas, we were able to prove the original theorem, that reverse of a reverse of a list is the original list itself. This is how you generally write proofs in Isabelle. You start off by writing a theorem, and then you realize that it doesn't have enough information, so you go ahead and write a lemma to help solve the subgoals, and that lemma might again need some more help, and you build on these lemmas, and you finally arrive at a point where Isabelle can solve the entire thing on itself and tell you that the theorem you originally wrote is in fact correct. So um, I hope this tutorial kind of helped you understand how you would work with Isabelle and how you could write a model of a program in Isabelle, and then write a theorem to prove the correctness of that program. And this is just a flavor of how Isabelle is used and it has a lot more functionalities and a lot more theorem proving capabilities that you can do. You can write your own tactics, not just induction. You can apply other rules to prove your theorems, and it has a lot of flexibility, and it's a very good tool that you can use to formally verify or otherwise prove theorems and many other things. So I hope this tutorial helped you all. Thank you very much for watching this.